Hello and welcome back. Today we are talking about section 4.2, which is called optimization. Now this is going to be a very short lecture. The exercises video will be a little bit longer. Please don't interpret that as meaning that this is an easy topic that you can breeze by. It's a topic where the ideas are very simple, so we'll only need a couple slides to introduce them. But just like 4.1, it requires a lot of practice to be able to do it well and to do it quickly. So one thing that's very common in lots of areas of science is that you have some function that measures some quantity and you want to know where it's largest or smallest. That's called optimization. These are, to find the points where they're largest and smallest, those are what we call the global extrema. Now in 4.1 we talked about local extrema, local minima and local maxima. Those are the points where they are lower or higher than all the little points around them. When we talk about global extrema, though, we're thinking about the whole big picture of the function. So here's an example of a function, and these solid dots at the ends mean those are the endpoints. So this function's defined on some closed interval from here to here, including the endpoints, and then stopping. So from 4.1, we know that we have a local max here, because this point is higher than all the little points around it. It's the top of a hill. And we know that we have a local minimum here. It's the bottom of a trough. It's lower than all of the little points around it. But we also have a global maximum and a global minimum. The global maximum is the largest point anywhere in the function. Because we have closed endpoints, those endpoints count. So this point right here, this is the global maximum because out of all of the points in the function, it's the largest. It's larger than this local max. It's larger than this endpoint. It's larger than all the others. The global minimum, however, is not an endpoint. It's this point right here. This point is lower than all of the other functions. So that's it. That's the new idea of this section, a global minimum and a global maximum. Here's an important fact that will help us find them. If you have a continuous function on a closed interval, so we have endpoints a to b, then you're guaranteed that your function will have a global maximum and a global minimum. This assumption of continuity is important, and this assumption of closed interval is important. For example, if we had a function, let's say e to the x, we know what this looks like, roughly like this. This function is not defined in a closed interval. It's defined all the way to negative infinity and infinity, which is not a closed interval. This function does not have a global maximum or a global minimum. A global maximum and a global minimum have to be an actual point. You can point to it. You can say, here it is, and this is its height. This gets larger and larger the further we go. So if we try to do that with any point, we just have to go a little bit more to the right and get a larger point. So you don't say that the global maximum is infinity. That's not valid. There is no global maximum. On the other hand, with a global minimum, you don't say that it's 0 because we're approaching 0. If the global minimum were going to be 0, you'd have to actually be able to point to a point of the function and say, here, its value is 0. But of course, we can't do that. Its value will never reach 0. It gets smaller and smaller forever. So this one also has no global minimum. So having one or both endpoints is important for telling you whether you're going to have a global maximum and a global minimum that exist. Now here's the strategy to find them. What we saw kind of from the picture on the last slide, let me just go back for a minute. Where are you going to find the global max and the global min? Well, they could be overlapping with a local max and local min. For example, the global minimum is this local minimum. So each of the local extrema has the possibility of also being a global extrema. Where you have a big difference is that the endpoints, if they exist, we don't consider those local maxes and mins, but they have the opportunity to be global maxes and mins. So our strategy for finding global maxes and mins is to start by finding the critical points, because we need to know where we have those possibilities of a local max and min. So we find the critical points, and then we don't need to worry about the first derivative test or the second derivative test or whatever to figure out if they're maxes and mins. All we need to do is plug in the x values of those critical points and check the height of the function. Now, if you also are supposed to find local maxes and mins, then you can worry about your first derivative test and your second derivative test and so on. But we don't have to worry about that here. Take those critical points and take the endpoints a and b if they exist. So like here they don't. Here they do. If they exist, take them as well. Take those critical points and the endpoints, just plug them all in. You'll get a bunch of values of f. The biggest one is the global max. The smallest one is the global min. It's very simple. We'll do one example right now, and then maybe a second example. I don't exactly remember what's on the last slide, even though I made it just a couple minutes ago. For this example, we're going to find the global extrema of this polynomial, and it might look familiar because it's the one that we did over and over again in section 4.1. Except we're going to restrict it to the interval from -infinity to 14. So this only has one endpoint. It's got an endpoint of 14, but not an endpoint on the left-hand side. The book has this example with actually a bunch of different intervals, but not this one. So I picked a different one from the book, and you're obviously welcome, you're encouraged to go look at the other ones in the book for more practice. So step 1, find the critical points. That means take the derivative, factor it, set it equal to 0, and solve. We did this already in 4.1 a bunch of times. We get -2 and 8. That's the critical points. We also think about the endpoints. We have no lower endpoint because it goes all the way to -infinity. In fact, I guess normally you would see this instead of a less than or equal to sign. I guess it would be more common to just write less than, although that's kind of just a notation thing. Really, when it goes to infinity, it's not an endpoint. But we do have a right endpoint, so that has to be considered there too. So we have 3 possible locations where the global min and global max can appear. All we have to do is plug them in, find the smallest and the biggest. Now, because we're multiplying by big numbers and cubing, I would not expect you to be able to plug in, for example, 14 on something like this on an assignment. So if it's on Wiley Plus, of course, you can use a calculator. I just already calculated ahead of time. So don't be worried by these big numbers. Just understand the idea. If you plug in -2 to the original function, you get 104. So that means at -2, this is not really to scale, but we'd have -2, 104. If you plug in 8, you get -396. So this is 8, -396. If you plug in 14, you get 360. 14, 360. And those are the only 3 points you have to worry about. So where's our global maximum? It's just the largest one, which is 360. So the global maximum is located at 14, 360. The global minimum is at the smallest point. So that's 8, -396. Okay, moving on. Oh yeah, so we don't have another example, just a little reminder here. These require lots of practice. So make sure that you're watching the exercises videos. Make sure that you're doing the suggested homework. And if you do those and you still feel like you need a little more practice, there are plenty of good exercises in the book that I don't pick for the suggested homework. So you can always just look at those as well and ask if you need any help with them. Okay, I'll see you in the exercises video. You thought the video was over, but actually I'm adding this little bit here because I realized as soon as I stopped recording that I said something very silly on this slide, so I want to go back and fix it. When you have an interval like this, which is partially or completely open, meaning one or both sides are infinity, it's a little trickier than I said. I made a silly mistake here. I said that the global minimum was 8, -396, and I drew this point here. But just looking at the graph, that's clearly absurd because there are all of these points down here that keep getting smaller and smaller. My definition of a global minimum was a point that has a value smaller than all the other points. Well, this can't be the global minimum if all these other points are smaller. So I absolutely should not have said that. What you need to do in this case where you have an infinity or a -infinity, we call that an open interval, you have to think about what the graph looks like and realize, like, okay, maybe this would be a candidate, but actually, because we know this is a cubic, its leading coefficient is positive, we know that it's going to go to -infinity on the left. So it doesn't matter how low this is. That tells us we're never going to have a global minimum because we'll just keep getting lower and lower here. So what I should have said is that there is no global minimum. So we had a fact that said, if we have a continuous function on a closed interval, then there's definitely a global max and a global min. There, what I said is correct. Check all the points. The biggest one must be that global max. The smallest one must be that global min. But when it's not on a interval, when it's not on a closed interval, you have this situation where you have to actually understand a little bit more about what the graph looks like to know This is the lowest point out of my possibilities. But if as I go towards the negative infinity, I keep getting lower than that, then this is not a global minimum. Okay, so sorry that I made that error. Hopefully you weren't too confused, and I'm just going to tack this on at the end of the video to try to fix my error. Okay, now I promise we're done with this lecture.